Yeah, you can ask me.
Sir, in IIT Bhubaneswar, sir, what is your MTech project or MTech project was there, sir? Or
Oh,
about what thing you are going to do?
what I did in IIT Bhubaneswar.
Sir, the project and all.
So it was basically I had worked on a curved beam. So curved beam for that there is something called as a spectral finite element method. So like it is entirely dynamics. So if you apply any impulse load on the beam, like a short load, just like a tap impulse load, so then how you are going to get the responses using the frequency domain instead of time domain, we use the frequency domain, and we get the response like displacement, velocity. After we apply the force, we get the displacement velocity of the beam, and from that response, we can deduce if there is any crack or if there is any damage, etc. on that beam. So that modeling uh, the beam and also getting the numerical solution of that. So that thing I have done. So it's like a finite element method if you have heard.
Yes, sir, I heard about it.
Yeah. Have you taken any course?
No, sir, in this semester it's not there. Maybe it will come in future, sir.
Okay.
Sir, after did this research, where we you apply all these things means the real time application or of these things of your research.
Real time applications are like I don't do it. So like I have done my research like whatever I could. Then I have published a conference paper. So it's not like whatever I have done I had to reflect suddenly tomorrow in practical applications. So I have done something. If someone finds it useful, they'll take that paper or something from that model. They can improve upon that and they can do some things. And the important part is like if you have any aircraft structures or any machines, and if you want to find out cracks on it, so like if the cracks are present on the surface, uh, what you say, the cracks are present, there are some brick cracks or something which is on the surface that you can see, then it's fine. Then it's fine, and also only just you can get a qualitative assessment, do the qualitative assessment that by seeing visual inspection. So we say that thing called as visual inspection. So you see any building and you see a crack and you tell that okay, this has some cracks, but you cannot tell something about that. But if you have, but if there are some cracks which you cannot see, like inside of the structure, which are not accessible, like you cannot go inside some parts and all, you cannot go and see. Okay, so that's for that thing we need something to identify those cracks and all. So and also you have to quantify the crack. How much how much deep is that crack, and how much effect is it showing on the structure's performance. So all these things. So see, I'll the whatever we do, all these things to main designing a structure is one thing, and after that we have to maintain it. So design, build, and we have to maintain it. So we have to do regular inspections or maintenance so that structure fulfills its design life satisfactorily. So because there are a lot of uncertainties in the nature, and also when we build, anything. So we cannot say that if I have built it today, it will go to its lifetime without any damage or something. So we have to design something. Then we have to designing. We take a lot of care. Then we build something like a machine or a building. That that time also we take a lot of care. So, but even though we do a lot of things, we experience some uncertainties in the nature, because nature is so unpredictable that you can't say that this thing will go on without any damage or something. So we have to regularly maintain. Suppose if we have constructed a bridge or a machine, something like that, we regularly do inspection that if this is working properly. So you go to a bridge and you see if there are any cracks on it, and if there are some damage, if there is some damage on it, something like that. So, but that is one type of inspection that is called visual inspection. It is like just saying the qualitative kind of thing, that there are some cracks, but that, and as I said, you cannot always see the cracks. You can only see the cracks on the top of the bridge. Maybe you cannot, maybe there are cracks inside, in some parts of the bridge, in some beam, like you cannot go and see that. So sometimes people use drones, like drones go in the inaccessible parts and take footage of that and all those things they do. Then also it is not enough. Like you cannot see some things like which are inside, which are not accessible by anything. So that time what we can do is we have to do some non-destructive experiments. So non-destructive experiments are like uh, you apply a small amount of force or small amount of something like disturbance to the structure, which is like which has very small amplitude, but the frequency of it is very high. So like uh, if you like, if I hit something like if I hit this box is there, if I hit something like this with high frequency but less amount of load, some disturbance is happening in this structure. Due to that disturbance, uh, a wave propagates through this structure. Okay, so high frequency load will make like very high frequency, like in terms you can say in kilohertz or something like that. So uh, you can say it, right? Like you can just feel it, like if someone hits you very suddenly, like you feel like your whole body gets vibrated, that kind of thing. Some disturbance is traveling to your body. So this kind of wave travels to your body. So when so what we do is, in non-destructive testing, one kind of non-destructive testing is that we apply a small amount of load, which is very small amplitude but very high frequency. If I apply it, and after that I will measure the after the wave travels, after the wave travels, if there are any cracks or discontinuities or damage in the structure, what happens is that some part of the wave gets uh, uh, some parts of the wave gets reflected to from that crack. Again, it comes back to the uh, again it comes back to the position where I have applied. So what I'll do, I'll have some accelerometer or some kind of device which measures the displacement caused due to my force. So I can put it anywhere. So I can see, uh, you will be continuously doing these experiments, because we say that these are non-destructive experiments. So non-destructive means I am not I'm not doing any damage to the structure. Okay, it is like a small amount of loads, very small load. Just I'm giving some vibration kind of a thing or a wave kind of a thing. It will not damage the structure. It will just produce a wave that travels and gives me the disturbances whatever happening in the structure. So I'll measure the displacement, and if so I will be continuously monitoring that displacement. So from start of the building, start of the construction to, let's say, like after 2 years you check, some crack has appeared. So there will be difference between the displacement which you have got at the initial stages when you have constructed or built the structure. When you have damage, the displacement which you get will be different. So by you seeing that difference, you can say that there is some abnormality in the performance of the structure. So you can have various methods, uh, based on the difference between the displacement or something else. Lot of things are there. Uh, so you can quantify like how much crack is. First of all, you can identify the crack has happened. First of all, that there is some crack or damage that has occurred. Then you locate the damage. Where is it on the structure? At what distance from the point of load application it is present? And then how much intensity the crack or the damage is uh, happening. And if I get this data, and if I get the estimate of how much the severity of the damage is, then I go to the field, then I go to the structure, and I'll do some maintenance like a repair work or something else, so that my structure doesn't get failed. So if you don't do this thing, especially for critical structures, like there are some uh, like if there are some you can see metro uh, elevated metro pillars and all those things, and suspended bridges, you can see San Francisco, there is one bridge, famous bridge, Golden Gate Bridge. Lot of bridges are there. So what they do is they continuously have some sensors present on the bridge. They have pasted sensors on the bridge, and they get the displacement of the bridge daily. They'll be monitoring like every time that is getting monitored. That is called real time monitoring. Every time they monitor the performance of the bridge, and if they see sudden, like if they see any abnormality, they get to know that there is some damage which is happening. And then they go to the bridge and they do some maintenance activity. If this thing is not done, if we don't maintain anything, like if we ignore there are cracks and okay, let it be, I have designed it for 50 years, then suddenly you might get breakage of failure of the structure, and you will have to bear loss of the property, life, everything. So structural, the thing the you can say that my project was on structural health monitoring. So application of that was this, uh, like you won't do everything. Like I have done the model and the given the model and the uh, solution, numerical solution of that. But we can say that like somebody else might be doing the experiments using this uh, analytical study which I have done. Analytical means I am solving it through mathematical models. Somebody might do the experimental study and he can match it, and okay, this is useful, then they can use it. So this is how research works. Like you cannot uh, like you can do research. I wanted to do experiments at that time, but I didn't have the time, and also because the MTech MTech program you have to complete, like project itself you get around 7 to 6 months. So you will be working very hard to complete it. Experiments uh, were initially in the plan, but I couldn't do it. Like there was no equipment also. So things like that. So have you understood? Mm,
Yes, sir, I understand.
yeah. So
Sir,
non-destructive.
we are eligible to attend the conference of where the PhD and the MTech or MSc means we are just seeing or attend the conference.
Uh, I didn't like what conference you want to attend. Mm.
So you told us that all the PhD students they get the chance of to represent their pet whatever they did
Ah,
research.
okay, okay. No, conferences are for everyone. Anyone can go to the conference. If you are interested, you can pay the entrance fee, and you can go to the conference. Like you don't need to present or something like that. Presenting is something else. Like you can just go and listen to the talks, or listen to the talks. That is a thing. So like UG people also go. Like if you like mostly people who have done some work, and they want to share their work to the audience, and conferences are like uh, meeting of all the people who are working on the same field. Like somebody, like conferences also happen for different topics, like for dynamics or nonlinear dynamics. One There are some conferences for composite structures. There are some other, and like for mechanics, like general, like all different conferences will be there. There, like you can see in IITs also, some low private colleges also, conferences will be happening. Uh, uh, like you can attend, like you just have to pay the fee, and you can, if you are interested in something, you can just go and attend. But I can't guarantee you that you will understand everything what they are saying, because like things will be so what you can say, it's not like you will get, like of course you will get to know the application and what they are doing and stuff, but the mathematical part and everything, you might not have like, even if I go to a conference which I'm not like doing research on, I'll not of course I'll understand the things, but I won't get everything out of that uh, talks and all. So main purpose of the conferences is that people go, like-minded researchers, they want to share their work, and they want to connect with other people who are doing like some work, and they want to collaborate in future, maybe like they can work together. So people go meet people, like there will be a lot of talks, and like keynote sessions will be there. Some professors, uh, like some notable professors will come to the conference, and they'll give talks that some breakthrough research if they have done, like those kind of things happen in the conferences.
Understand, sir.
Yeah, and do this.
Understand, sir.
So whatever we have, you learned dynamics, um, have you gone through dynamics in your BTech?
No, sir. Still now statistics is going on only.
Okay.
The fourth semester will come dynamics and also.
Okay, you do have dynamics. Okay.
Yes, sir.
Okay, maybe like single degree of freedom systems you might study. We will see some. So, okay, we'll just go through what I think you might have seen the review lecture by the professor, from the professor itself, right? The last
Sir,
lecture.
the
Uh,
review lecture is not open, sir. It is paused. I don't know why.
oh, the last
Yes,
lecture is
sir.
not open.
I tried to three times, but I don't think so. It is open because it's paused.
Ah, okay, I'll see. Let's see. What happened? Okay.
Now open, sir.
Oh, it's opening. Huh? Okay.
But I don't know why. But on the time it is loading, loading,
Okay.
loading
You
page, and
just
it's.
You don't need to go through this thing only. Like you can just go to YouTube and open.
Okay, sir. Because it's showing loading, loading. So I seen the
Uh,
all our videos are opening, but why it is showing loading? So I give it two, three time I try, then after.
okay, you might go and see after this. It's like so in this course, first like uh, things. Let's see what we have learned. So we have seen like in engineering mechanics, whatever we have learned, mostly it deals with rigid bodies. So, okay. In engineering mechanics, like like rigid body motion, everything related to that we learn kinematics, kinetics, all those things, statics, everything. When we go to friction and all, different things we learn in engineering mechanics. Uh, Strength of materials. When we go to strength of materials, we go and study about the deformation of bodies. So in nature, you can't say that bodies are every body is like a rigid body. Like we can't assume like, and also no body is a rigid body. You can say that it is nearly rigid, but everything deforms when like depends upon the load. Like if I have a rock and if I apply small load, then you can say relatively it is a rigid. But if I apply high amount of load, uh, then it is not rigid. It does deform. So it depends. Like it is just an you can say that assumption kind of thing that sometimes we assume some bodies as rigid depending upon the amount of load which we are applying. So so it is very important to learn about the deformations or deformations in the bodies when we apply the loads. So so remember that deformation is some people like I'm just saying it. Some people just sometimes forget that the deformations and displacements are different things. Okay, deformation is bodies. If I have a body like this, let's say a square something like this, and if it is getting its getting its shape changed like this, let's say uh, something like this, just a representative figure. So you can see, let's say these are 2 points on the body, and after the deformation, they are getting displaced. Points are getting displaced, and initial positions of them are not the same as the deformed positions. So this is deformation. Displacement is something when you when a body is present here, and if I push it like without getting deformed also it can get displaced. Like you like when we talk about rigid body motion, there we say about displacements and all. Okay, so deformations is something when a body uh, uh, different particles on the body uh, uh, go away or some go near to each other due to the applied load, and their positions get changed. Particles on the body get their positions changed. So that thing is deformation, and it is strength of materials is mostly about all of these things. So whenever a body is getting deformed, so due to the deformation, uh, due to the deformation, so if it is getting deformed, it is storing some energy. You can say that It may be called as strain energy. Like if you can just say I have a spring, and if I apply a force, so it gets deformed, and when it gets deformed, it is storing some energy. So half kx square, we say that, right? So if I release this force, it energy is getting released and it goes back to its initial position and the energy is lost again. So whenever there is a applied force, if there is deformation, energy is getting stored. So due to the displacements, like due to this energy which is stored, so different, like due to the applied force, like if I have applied some force, there should be some resistance. So of course it will make the body deformed, but still there is some resistance in the body due to the applied force. So in spring you can say that that is a spring force. Like if I apply some load, there is some stiffness in the spring which is resisting this applied force. No, otherwise, if I don't have any stiffness, like this spring has to go infinitely, like it will go just infinitely to this. Okay, so there is some resistance which is happening in the body. Like if I have a bar, let's say, uh, if I'm applying some load, so due to the applied load, if this bar, like let's assume that this bar is like this load is small compared to the failure load. Like it's not, we have not gone, like we are gradually applying load. So this bar may get deformed, like this its length may increase, but the particles between the particles in the bar are trying to resist this force. So due to this energy which is stored, and also stress is uh, strain is getting induced in the bar. So when there is strain getting induced, obviously there is strain in the body. So sorry, obviously due to the strain there is stress in the stress occurs in the body. So stress is nothing but resistance to the applied forces in the body. Let's say if I cut this, and if I cut a section, like there will be some resistance, that is the strain which is occurring on this bar. So stresses, strain is induced due to the applied load or deformation, something like that, and due to that strain we also have the stress. So this is when we apply the load. Let's say if I have a bar and if I just heat it, if I just heat it, there is only strain. There will not be any stress. So if I heat a bar, if I heat a metal bar, let's say, it will get expanded due to rise in temperature. We know that that is a property of metals. Like they will expand when we heat them. So if I am applying it, if I am applying the heat and there is no constraint on the body, it will just expand freely, and you can say that strain is there, but there is no stress because it is the inherent property that it has to expand. But if I'm resisting this expansion of the body, let's say if I have a cantilever beam, and if I am increasing the temperature and I'm also fixing this side, this bar wants to expand, but I'm not letting it expand because of the support which I have put it here. So due to that, uh, the deformation which has to occur due to the rise in temperature is not happening, and you can say that this fixed support is again uh, uh, pushing this bar to its initial position. So due to that, strain will occur. So when we restrict the temperature strains, we get the thermal stresses. So and then we have first seen what is a stress tensor. Stress tensor is like whenever uh, whenever we have a body, whenever we have, let's say, some body, and if I take a small point on the body, infinitesimal infinitesimal dimensions, like if I take like delta x, delta y, delta x, delta y, and delta z are very small. So it has stress uh, which can be shown like this. State of stress can be shown like this. Uh, like normal stresses are there, and also shear stresses are there on this small point also. So stress tensor is having 9 components. So we go from sigma xx, sigma yy, sigma xy, sigma xz, and sigma yx, sigma yy, sigma yz, and sigma zx, sigma zy, and sigma zz. So, or you can write this as sigma ij. So initial notations, I think, if you remember it good, but it doesn't matter in this course. But yeah, so 9 components at each point for a 3D. This is for a 3D body, 3D deformable body. You can get 9 components uh, in the stress tensor. That's why it is called as a stress tensor. It is not a vector. Stress is a tensor. We have to remember that. Similarly with the strain. So we also here too we got the 9 stress tensors. Remember important things to remember. And we have also seen what are the relations between the stresses and strains. Like we have seen that sigma ij is equals to E into epsilon, right? So this is called as the elasticity tensor, and it's like uh, it's like for some, generally it has some, you can say 3 into 3 into 3 into 3, 9, 9 3 is 27, into 3 81. But if I go to a isotropic body, I can do the deductions and all. I can say that we have only in this stress tensor we have only two dependent elastic constants. So elastic constants are, we have got this elastic constants E nu G K. Hmm. This is Young's modulus, this is Poisson's ratio, this is shear modulus, and this is the bulk modulus. Bulk modulus is uh, volumetric stress by volumetric strain. this this all these are the four things which we get for an isotropic material. In all the directions these properties will be same. So uh, so that's why I get 4. But again, if I have only 2, I can get the other 2. So we have the relations. I think E is equals to 2G into 1 plus no, and E is equals to 3K into 1 minus 2 no. These just verify it. I think these are correct. There is something something is wrong in this relations. You can take it. So if I have 2, I can get the other 2. So I can, but this K doesn't come in this elasticity tensor, so we don't need to get this uh, elasticity. If I have 2, I can get the other 1. So other like using 2, we can get the other 2. So only we have for isotropic materials, we have 2 elastic constants, and we there is some. Uh, Can you tell me the difference between a homogeneous material and an isotropic material?
What
Do you know this?
Sir, whatever I know, I tell that. Sir,
Yeah.
homogeneous means we consider the property of the material is throughout is same.
Ah.
That means the physical property, and there is no discontinuity. Nothing is there. So that is
Ah.
the homogeneous and
Okay.
isotropic. Uh, Little confused. I'm not sure.
Okay. So let's say, Priyanka, you want to say?
Isotropic means along any direction the property will remain same at a point. But I
Okay.
think it will differ from point to point, but at a point it will, in any direction it will be same. That is isotropic.
Okay.
And I think that homogeneous means at each point the properties remain same.
Yeah. Yeah. You are right. So isotropy, as she said, if I take this point, like let's say, if I have this bar, and if I do this tension testing by applying loads in this direction, uh, like let's say this is some infinitesimal bar, like just assume it. So, and if I'll get some Young's modulus for this, like if I'll get the tension test, I'll draw the stress strain curve and I'll get the Young's modulus. Again, if I apply this, okay, again I'll take the same bar, but let's assume that I'll take the same bar, but I'm applying the load in the other direction instead of, let's say, x, and I'm applying the load in the y direction. Now if I apply, now if draw the stress strain curve for this bar, you can say that I'll get some Young's modulus for this. I'm just saying Young's modulus. It can be, you can also measure mu also. Uh, you can get the shear modulus, whatever, something. Young's modulus is easy because you can get just directly get from the stress strain curve. So if this thing remains, like E remains same in x direction and also in y direction, and also if I do in z direction, for this, let's say this is very small bar, okay, from a very big thing I'm just taking a small thing, okay, from just, you can say that this is a point, okay, like if I have a very big beam, like I can take a small strip of it and I can do the testing, right? Just like you can consider it as a point. It is not a point, but you can say that it is a point. So while we do the tension testing, the specimens are so small, like some, I don't know, I forgot the dimensions. ASTM standards you have. So in different directions, if this property of E remains same, I can say that material is isotropic for this. Okay, material is isotropic. E and nu, everything has to be same in different directions. E nu, G, K, everything has to be same. But if this thing, you say, like I say, if I take a wooden bar, uh, if I take wood and if I apply load along the direction of the fiber, I'll get very high Young's modulus. But if I apply it perpendicular to the directions of the fibers of the wood, it will get fail easily. So properties of, E will be different in this perpendicular to the direction of fibers, and E will be different in the perpendicular to the direction of parallel to the direction of fibers when I apply the load. So different nu is occurring. So that is not an isotropic material. In fact, wood is considered as orthotropic, because in, let's say, if along the direction of the fibers, uh, uh, this is I have Ex and Ey and Ez, because perpendicular to the fibers, I can apply in this direction or also in this direction. Ey and Ez will be same. So you can say that that is orthotropic. Let's say if I have composite material, uh, then things can be like, in X direction it will be different, in Y direction it will be different, and in Z direction it will be different. Something like that you can get. So that is called as a isotropic material. If, let's say, steel is there, In steel, you can apply anywhere, like in any direction. It will give the same Young's modulus. So you don't need to like we can say that that is an isotropic material. Let's say if I have a material and if I go from here to here uh, and I take the test, and if I get the Young's modulus uh, or something or all the properties are same as this bar, then I can say that these are homogeneous. But if I get some other Young's modulus and other material properties, uh, I can say that this is not a homogeneous material. So isotropy is a point property, whereas homogeneous is about like different points on the structure. Homogeneous. So homogeneous means like you can say that the same material is present everywhere on the body.
Understand, sir. Sir, means generally homogeneous means it is the the constituents or the mixture of the element are everywhere same. Means,
Yeah, like you have a concrete beam, like everywhere the same concrete is present. Like say if you have some a steel and aluminum beam, like it's not homogeneous, like something kind of thing. Okay.
understand, sir.
Sir,
Yeah.
so when you said about homogeneous, like if
Yeah.
at point A, if like the property is 2 units, like for example, at
Hmm.
point A it is 2 units along x direction. So at point B also it should be 2 units along x direction or any direction for
No,
homogeneous.
at point A, if it is 2 units in the x direction, at point B also it should be 2 units in the x direction. In y direction, at point A, if it is 4, at point B also it should be 4.
Okay, sir.
Yeah.
Okay.
Is the difference between homogeneous and this thing a lot of people get because this will be asked a lot in interviews when you go and all. So we have seen this. Uh, we have gone through stresses and just see what where we have started. So we have first got the stresses. We have learnt about stresses and
Sir,
yeah.
sir, is it vice versa is true? Either a homogeneous material called as a isotropic material or either a isotropic material called as a homogeneous. Vice versa is true.
No, no, they are the different things.
Generally, isotropic is talk about when the it is generally everywhere the forces are same.
No, not the forces. Elastic
Means
properties are same
okay.
in different directions.
And in homogeneous, it is talk about the physical property only. Means everywhere.
No, physical and also this material properties are same. Like at different points on the body, material properties are same.
Okay.
Yeah. So we have learned about stresses, and also we have seen like numerically we have seen about stresses. We have seen about something called as principal stresses. So principal stresses. So we have seen the stress tensor, and then we have seen principal stresses. So principal stresses are something like if I have a stress, like if I have a body which is subjected to stress like this. So I have taken like from a body, I have taken this element, and there are some stresses acting on this body. But I can take I can take the orientation of this element in different directions. Like I can take it like this. I can also take an element like this, something like this. In different orientations, I can take the element. So when the orientation changes, stress components also changes. So here, if you get sigma x, here it will be some sigma x dash. You can say something like this. Orientation changes, stress components also changes. But the main thing about if I have taken this if I have taken state of stress at a point, regardless of this components in the stress tensor components will be different, but there will be things which will remain same for this stress tensor. Those are called the three indeterminants. Indeterminants we have learned, right? First is the determinant of the stress tensor. First is the sum of the
Three
uh,
summation.
principal diagonal elements, and second one is the minors of the principal diagonal elements. Okay,
Yes,
and the third one is the determinant of the stress tensor. So I1, I2, I3. So if I am taking a stress tensor if I am taking an element at a point, and sorry, if I am taking the state of stress at a point, regardless of the orientation changes the stress components, but this invariance will remain same. So if someone, let's say, gives you uh, two stress tensors and different stress tensors of having different values in them, and if they ask you that can you say that these two stress tensors are for same point, by looking at the stress tensors, if you say that these are having different values, uh, so that's why these are for two different points, then it is wrong. You are just you have not that means that you don't know what is the property of invariance. So you have to take those two stress tensors. Let's say uh, sigma 1 you will take some value a b c d, numerical values will be there DHL. And here sigma 2 you will get some capital A B C D E F G H I. So because the values are different, it doesn't mean that uh, they are for different points. I mean, they may be for different points, but if they if they are saying, let's say that these two are for different points, is it true or false? Then you have to check the invariance of this and check the invariance of this, and if the invariants I1, I2, I3 of this sigma 1 are equal to I1, I2, I3 of this sigma 2, then you can say that the state of both the state of stress can represent a single point. Okay, this is just because we are taking different orientations, we are getting different components, but invariants will remain same if I am taking a state of stress at a point. Okay,
yes, sir.
okay. So if I am taking if I am taking this some orientation, if I am taking a different orientations at some orientations, I'll get a state of stress such that I'll have only normal stresses in these planes. uh, at some particular orientation, I don't know what is that orientation, like I have to find out. At some orientation I'll get only normal stresses, so that is those are called principal stresses. Okay, so principal stresses means these are the maximum normal stresses which I'll get uh, for uh, for this stress tensor. Like I can just sigma xy sigma yz, I can just I can just rotate it with respect to some orientation. I don't know what is the angle of principal planes, and I'll get the stress tensor as this sigma 1, sigma 2, sigma 3. So I'm getting only the principal stresses. So if I take just a 2D body, I can just draw more circle. So more circle, I think you don't. If I want to do it graphically, it is a very easy thing. So like uh, I can also remember the formulae for principal stresses for a 2D element also very easily. So what I have to do, I have to just first draw sigma x on the graph. So this is the normal axis, x-axis is taking normal stresses, y-axis is having shear stresses. So I'll draw sigma x, sigma y, and then I'll draw this is shear stress. Similarly, on this plane, sigma y plane, this is like clockwise. So anti-clockwise I will take negative, and anti-clockwise clockwise I will take positive. So I'll draw the shear stress at this point, and simply I'll join this. This is my radius, and I'll take a protractor and I'll just draw this. Okay, and the point at which this intersects, this circle is intersecting the x-axis, the normal stress axis, where the shear stress is 0, is my maximum principal stress. At this point where the shear stress is 0, but and also this is the minimum on the axis which the circle intersects. This is called as minimum principal stress, maximum and minimum principal stress. Can just write the formula, right? Like I can just use this. Uh, if I want to find out this point sigma x or sigma 1 or sigma 2, I can just first find out the midpoint of. I have 2 points, okay, on the x-axis, sigma x comma 0 and sigma y comma 0. So these are the Cartesian coordinates of this points, you can say. So sigma xx, sigma yy. So I'll first find out the sigma xx, sigma yy, midpoint of this 2 points, sigma x and sigma y. Yy is this point, which is sigma xx plus sigma yy 2. And if I want to find out this, I have to find out this radius, right? So this is the radius of the circle. So this is also the radius, right? This line is also the radius. So here I know sigma x and here I know tau also. So sorry, this length I know, which is sigma x minus sigma y. So only this length is sigma x minus sigma y, and I know tau. So this is a right angle triangle, and I can simply write. Sorry, this is sigma x minus sigma y by 2. Sigma x
Yes, sir.
minus sigma y by 2. Okay.
Yes, sir.
So sigma xx minus sigma y by 2 whole square plus tau xy square. So if I add the radius from this point, from the center midpoint of the circle to the, if I add it, I'll get the maximum principal stress. If I subtract it, I'll get the minimum principal stress. So using this graph, I can simply remember it. I don't need to mug up this formula. So that's the one you can say. Uh,
It is very easy to remember to if you forgot, draw the circle quickly and do it.
yeah, quickly and do it. Like you can just remember. So if you do this in interview, people will get very impressed. Like, okay, how can like you instead of like you can say, but they might But if you forgot and if you just try drawing the circle and noting down this all these details, and if you get this, then people will get impressed. Okay, this guy knows something or this girl knows something like that. Okay, so and the orientation of the principal planes is, let's say if this angle is theta, in like you can calculate this angle, like if you know the uh, uh, points, like I can simply calculate the angle, like I know this and this, so tan theta I can take uh, tau by sigma x minus sigma y over 2. So this is just 2 tau by sigma x minus sigma y. So whatever the angle I get, so it is in Mohr circle. This angle is double of. So this is my initial element. So my principal planes will be. Let's say I'll just write it as 2 theta. Okay, I'll just write it as 2 theta. So whatever the 2 theta which I get in Mohr circle, it is actually the orientation of principal planes from the initial planes is half of the orientation in the Mohr circle which we get. So this is my initial plane and this is my principal plane. So this is present at some angle theta with respect to that. And remember that each point on the Mohr circle uh, gives me a plane uh, on the gives me a particular orientation of the plane. Okay, so I can keep moving it. So I'll get like for a same body you can take like different planes, right? Like at the same point I can take orientation like this, different orientations as I wish I can take. Nobody is restricting me. So it depends on my convenience. So using Mohr circle, like Mohr circle will give you uh, on what plane, what is the stress. Simply using the circle, you can say that on this plane, uh, this is the what you say stress which is occurring, like without much calculations. Like you can use stress for transformation using the stress tensor and all. That is like more complicated thing. If I know the Mohr circle, I know the orientation. Like if I have this plane, I want to know at theta degrees from the initial x plane what is the stress acting, normal stress and shear stress. I can just use the Mohr circle and I can get that. So things become very easy, you can say. So principal stresses are this thing, and also we have also seen about 3D Mohr circle. So 3D Mohr circle is something like you get this, and you remember this shaded region. I don't want to go too deeply into this because not the scope of this course. But we have sigma 1, sigma 2, and sigma 3. This is sigma 1, this is sigma 2, and this is sigma 3. So we have to remember that always sigma 3 is the minimum principal stress. Sigma 2 is intermediate and sigma 1 is the maximum principal stress. So this shaded region, any point like on the periphery of this inner circle, on the periphery of this inner circle, and also in this entire shaded region, if I take any point, it will represent state of stress at some plane on the 3D body. So a 3D element at a point on the body. Okay. So for 2D only it is on the periphery of the circle. For 3D on this entire shaded region, we take the uh, if we take any point, it gives the state of stress at some plane on the body. Like 3D, you can imagine like there is some 3D body, and you can take a plane like this, or you can take some plane like this, which is in this body, or you can take some plane like this. So can take any plane. So lot of planes I can take. So depends. I have to know for 3D thing. I have to know the uh, what do you call direction cosines of the normal of the plane. Okay. So direction cosines are like if I have some vector or a normal. So these are nothing but what is alpha, what is the x-axis making with the normal, what is the y-axis making with the normal, and what is the z-axis making with the normal. So the important thing which we know is about that squares of all these cosines, sum of squares of all these cosines should be equal to 1. All these things are you might have learnt in the 11th or 12th grade. I'm just saying. So L is cos alpha, cos beta, cos gamma, like this. For a 2D, I can just have one angle. I can get the orientation. For 3D, I need these three direction cosines to give the orientation of the plane. Okay. Then we have why do we need principal stresses? Like can you say can you tell me, can you like what do you have understand, what have you understood uh, from the principal this the thing which we have discussed, principal stresses? Why do we need principal stresses?
Sir, because when we apply the forces, there is the combination or resultant force will come where uh, the the maximum tensile or compressive stress is maximum there. So that's why, sir.
Hmm.
So it is uh, helpful for us to find out where the if the stress is maximum on that plane, so it will
Hmm.
generally crack or failure happen on that plane. So that is the way.
Yeah, very good. So that is the most important thing which we have learned that using the principal stresses, we can generally get an idea about in which plane the maximum, if something is maximum on a particular plane, it means that it has the most probability of failure occurring in that orientation. So we know, we want to find out where it is happening. Let's say if I have a beam, I'll just tell you a standard. Like if I have a beam, something like this, and I'm applying 2-point load on this. Okay, is so how will the uh, what do you say, how will the bending moment diagram will look for this? If I want to draw the bending moment diagram, how will it look?
Sir,
First, first tell me what are the reactions which you'll get here.
so P and P both are.
Okay, how will be the bending moment diagram?
Sir, it is. Again, I tell, sir.
Trapezium, sir.
Yeah,
Yes, sir. Trapezium.
trapezium. How from this end, if I go, how it will be? Okay, it
Linear.
will be linear. Okay, up to this point.
Yes, sir.
Yeah. So it will linearly increase, and here it will be constant. Because why is it constant? Why is
Because
it constant in this section? Yeah,
because shear force is zero in that section, sir.
yeah. Because shear force is zero, bending moment is constant here. Okay. So, and if I draw the shear force diagram, how will it look?
Two box at two ends.
Okay. It will look something like this, right?
Yes, sir.
Again, we have to be consistent with the sign conventions. Okay. Think we have taken this sign convention only, I guess.
No, sir.
No.
Ulta.
Okay. Uh, just what is the sign convention we have taken? Just see.
Correct, sir. Sir, it is correct, sir.
Correct? Yeah.
Yes, sir. Yes.
Okay. Okay. Hmm. So we take this sign convention, right? It's positive. Okay.
Yes, sir.
So you can see if I take a small element here, how will be the state of stress? Uh, how will the state of stress look like for this element?
Tensile.
Tensile. Okay.
No, all components are zero, sir, because no shear stress is there. Nothing
No,
means
but you do have tensile strength, right? You do have tensile stress, right? Because this is a pure bending zone.
yes, sir. Yes, sir. The fiber has
Due to
come
the bending
tensile.
stress, yeah, if it bends like this, top fibers will get compression and the bottom fibers will have tension. So you will get the stress tensor at this point like this, okay? And there are no other things. So you can just draw this. You can this is something which you can something which you will get asked a lot in the interview. So they'll ask you the stress tensor. This is the stress tensor. It will stress or you can say element you can say, and state of stress. This is the state of stress at that point. And if you draw the Mohr circle, you can say that just you get sigma x is there, which is tensile, and everything else is zero. So this is my Mohr circle. So sigma x is my principal stress. Okay. and my minimum principal stress is 0 here. So I don't get any
Shear stress.
shear stress. Okay. So what happens is that if I apply load, and if I apply the load gradually, and my bending moment is increasing due to the increase in the load, and this stress reaches the yield stress of the material, then cracks will happen perpendicular to this like this. So my cracks will be appearing like this, okay, in perpendicular direction. Due principal stress is in this direction. That's why like this I am saying for a concrete bar. This, let's say, this is a concrete beam. Uh, am I able to? Am I audible?
Yes, sir. Now in between, I think the network issue.
Okay.
Now, okay, sir.
So the cracks will be like this, okay. But let's say if I go to this point, like which is near the support, okay, not exactly at the support, you can say just near to the support. So what is happening here? So and also remember that if I take an element here, okay. Priyanka, are you able to hear me?
Yes, sir.
Okay. So my bending stress will look like this. Sorry, the other way around. My bending stress will look like this. So tensile at the bottom and compressive on the top. Okay. So if I take an element here, there is no stress, and if I take an element here, there is compressive stress on the top. And shear forces are obviously here, nothing is there. So if they say that if someone asks you draw the Mohr circle for this, it is just 0, is a point. Uh, Mohr circle is a point, nothing is there. And if you are asked the Mohr circle for the top fiber, then it looks like this, 0 and sigma x. Okay. Since concrete is a brittle material, if this if this goes to the ultimate stress, my stress, tensile stress goes to the ultimate stress. So concrete has less, brittle materials have less tensile strength. So this part will have cracks. This part uh, you can say, concrete will be showing cracks like this, which are perpendicular to this uh, direction of the beam. Okay. Then if I go near to the support, you can say that bending moment is almost 0 here. And let's say we can just ignore this bending moment. I can just say, okay, it is 0. Okay. And but you can see that shear force is maximum here. Okay. At this point, at the support, shear force is maximum. And if I take a element here, if I take a element here, let's say if I take a element here, what will be my how will my state of stress look like?
Shear.
Sir,
Hmm? Shear. Are you sure? I'm taking here, okay, on the bottom fiber. I'm taking a point on the bottom fiber.
Zero shear, sir, and
Yeah, zero
tensile.
shear and
Tensile
zero
stress.
shear, tensile.
Tensile stress is there, but shear is zero.
I'm saying that it is near the support. There is no you can say that bending moment is almost zero.
Okay, at the support. Yes, sir. Zero, sir.
Yeah, everything is zero. Okay. So for this, there is no stress at this point. But if I go on the top, what will happen? On the top, what will the state of stress look like? What stresses I might get here.
Zero. Everything zero.
Everything is zero. Yeah. If I take element here on this on the neutral axis or at the center of the beam, uh, how will my state of stress look like?
Maximum shear stress.
Maximum shear stress. Yeah. So shear stress is there. So in between, if I take, how will my state of stress look like? Like here, if I take, let's say, how will my state of stress look like? What will I have?
There'll be shear and compressive, sir.
Yeah, there will be shear and compressive. Okay. So as you can see at support, there is only pure shear stress. Due to that, you can say that cracks will be occurring like this here in this direction. So you can say we have seen that due to the pure shear stress, I'll get something like this. Uh, It can be converted into this state. Pure shear stress can be converted like this. So at 45 degrees angles, uh, uh, if we rotate, we'll get the principal stresses. Like if I draw the Mohr circle for this, we know that we'll get we have zero normal stress, shear stress, zero normal stress, shear stress. If I draw it like this, at 90 degrees in the Mohr circle, but in the actual structure it is 45 degrees with respect to the initial plane. I'll get a tensile stress, tensile maximum principal stress and a compressive minimum principal stress. So that's why here, because the shear stress is maximum, I might get cracks like this. So in between that, crack directions will be something between 0 and 45, uh, like this. So this is how cracks will look like. Cracks directions will look like if I take a concrete beam. Uh, this thing you can expect something, some kind of questions. All these like tricky kind of things. Like you can be asked to draw the state of stress and draw the Mohr circle uh, in the uh, interviews and all. So and also competitive exams, you might expect some kind of questions based on these concepts. So I have got this like whatever I have told, I have got asked the same question here in IIT Madras. Not the same one, but the similar question, like drawing the state of stress, and a lot of people get it because it's like very easier thing when you do the interview online. It is easier to ask this question, and also you can get you can confuse the candidate a little bit. So principal stresses, everything we have seen, and also we have seen uh, a way to measure the stresses. So obviously we cannot directly measure the stresses, but we have this phenomena called photoelasticity. Using that, we are using the refractive property of the materials uh, to get to get the refractive using that, and also using the polarized light polariscope. So we are getting some fringes. So that fringes are obviously like that fringes are similar to the sigma 1 minus sigma 2, which is uh, the maximum principal stress minus minimum principal stress contours. These fringes will be similar to those contours. So if I have a axial load applied like this due to the axial stress, if I like at the point of application of load, some irregularities will be there. So we just go a little bit far from the application of load. That is called as Saint Venant's principle. This everything will get the same color. Okay, like for axial stress, we'll get same color fringes. Like you don't like you will get the same color. Like but if I apply a bending stress, like if I apply bending, like pure bending, I'll get different color fringes from top to bottom. Like on the top, it will be black, but here you can see different. And these fringes are placed like are at equal distances, so that's why you can say that this bending stress is linear here. So photoelasticity uh, is helping us to measure the stresses. Like obviously we have got a lot of because the because Professor K. Ramesh works on photoelasticity. He was very intrigued to show you all the things which he has done, and also like we have got to learn a lot of like we cannot practically see these things, but using this beautiful phenomenon, we can see how the stresses are varying in a material in a practical sense. Like uh, it is like as professor said in the lectures, like nothing can exactly replace the experiments. Like we can do numerical analysis, like you can do like if I want to design a structure, I'll get some mathematical model and I'll do the analysis. But even though if I do like if I like even though if I want to do a very detailed analysis, I'll take some assumption at some point, or your calculation will have some truncation in the decimals or something else. Like and also it is not possible to analytically solve. Like when I say analytical solution, like if you have a differential like uh, can you integrate everything? Can you integrate every function? No, right? Like sometimes we cannot integrate some functions. Like it is not possible. So we just go for numerical integration techniques. You might have seen the trapezoidal rule, Simpson's rule. You might have learned. That's why we go for numerical methods. Like you might have seen in your undergraduation. Like we have a separate you can say a course on numerical methods. Like sometimes it is not possible, like we don't have some exact solutions, so we go for numerical solutions. So numerical solutions also are not perfect. Like it will give you a near answer, it is not perfect. So things become very complicated when we go for large complex structures. So even though I do a like very good analysis, I might miss something. So it's like experiments. If I do the experiment, I'll get to know everything very clearly, because I'm actually doing the applying the load on the structure. I'm getting the details from it. So, but the thing is, all like obviously you cannot do the experiment on like every structure. Like I cannot build a plane or a spacecraft, something like this, and entirely I cannot. Like do experiments on it. So like it's not possible. I have to do the numerical analysis, do the analysis using the mathematical models, everything. Uh, like everything. Like if you even if you do in a software like an Abacus or something, an ANSYS or something, obviously doing the mathematical calculations, because instead of you doing the mathematical calculations by hand, the software is doing it in the background. You are just giving the CAD model, and everything is done by the software. So, and you are just giving the loads, and it is doing the calculations for you. Even though like we do these things, so doing experiments is very uh, a costly thing. Like you cannot manufacture everything and you can do the experiments. So we need, but sometimes we do need the experiments, like at least a little knowledge of experiments, and also if I have the analytical uh, thing, which like we have whatever we have done, like this Mohr circle, everything, all these things are numerical or analytical things, getting the bending moment diagram, everything. So we, in order to do these analytical things, it is not like humanly possible to take every detail. So we make assumptions, like in Euler-Bernoulli beam theory, we just ignore the shear stress because it is like not like very huge. So we just ignore it. So, but if I go to a beam which is having like very high depth, I cannot just simply ignore it, because things will be different. So then we have like gone to strains. I think strains, we have seen how we measure strains using the strain gauges, strain rosettes, different kinds of strain rosettes, and principal strains, and a lot of things we have discussed, lot of strains we have discussed. And then we have gone to the axial let's see, strain measurement, and then we have seen the tension test. Tension test is like a very good test which we use everywhere. Uh, like we want to get the yield strength. Like it is a uniaxial test, like but it is very useful. Like you can get a lot of things from that. So and also we have seen like we can use, obviously I can use the strain gauges to measure the strain, but using the strain gauge you can get only the strain at a single point, not a point, but at a particular area. Like I can apply the strain gauge at some point, but it will give only the strain at this point. But if I want to get the strain like whole field strain, like full field strain details, I can use the what is that thing? What experiment we can do? Like, do you remember that what was discussed in the class, or should I say it?
So the reflective electricity something.
Reflective photoelasticity is like an indirect thing. That is
Okay.
also one method. Other thing which we have seen, it's like very important thing, and it is very nowadays it is being used very uh, extensively. Like, want to say it? Anybody?
So some digital methods,
Yeah,
digital
yeah,
image something.
yeah. Digital image correlation we use. Okay. So what happens in digital image correlation is that we take the sample and we coat it with speckles, some small dots, black dots. You might have seen, like professor has shown this in the class. And as you apply the load gradually, as we increase the load, there will be some camera which we set up. Like if this is a 2D thing, there will be only one camera. If this is a 3D thing, we'll have two cameras. Like if this is a 3D structure. But if I want only a 2D thing, I'll just put one camera like this. So as I apply the load, the distance between this uh, speckles will be uh, increasing or decreasing. Basically, they are changing position. So I I'll be taking lot of photographs. Like some camera will be having like very high frequency, like 150 fps or something. I don't know. Uh, lot of photos are taken, and there will be some software uh, which the manufacturer or the digital like you will get entirely in one package, like you will get some software, and it will give you the displacement gradients. We know what is the displacement gradients: du by dx, du by dy, so dy by dx. So all these things we can get, uh, and using this we can get the rotations, and also like displacement gradient. I think you know that it can be decomposed into a rotation tensor and also uh, a strain tensor. So this is my strain tensor. So that's why I get like uh, we get like dou u by dou x plus dou u by dou x 1 by 2. I'll get dou u by dou x. So epsilon x is just simply dou u by dou x. So if I have xy, I'll get uh, y here and x here, something like this. So u and v. So displacement, if I have the displacement gradient, I can get the strains from this. So for every point on this specimen, I can get the strains using the digital image correlation. So that is one technique to measure my strains. And this is remember that uh, when you are putting the strain gauges on the specimen, you have to deal with a lot of things, temperature of this and that, and you have to apply properly with glue. As it was said that people are employed only for doing this thing, like just to apply the strain gauges. It is a very skill based thing. But here we don't need to we don't need any, we don't need to we don't have to contact the material, make contact any material to do the measurements. So that is one important aspect of this digital image correlation. So and then we have seen stress strain relations. Stress strain relations, obviously, whatever I have said, this is the stress strain relation. We have the elasticity tensor. We have seen how we get this using various explanations. So stress strain relations, and then interrelation between the different elastic constants, thermal stress we have seen, and then we have gone to now we have learned about stresses and strains, and then we have gone towards different kinds of deformations which might occur. So first we have seen, we know already we have learned, like we might have learned about axial loads and axial deformations. Now we have gone towards torsion. So in torsion, we have seen how we get the torsions, like, and also we have only seen in torsion, we have only seen about the circular sections, torsion in circular sections. So because what is the difference if I have a circular section and if I have a rectangular section, and if I, let's say, apply twisting moment on both the shafts? So what will be the difference which I will encounter?
Sir, in the square shaft, if we twist it, then the planes are not
Hmm.
the
Yeah, yeah, yeah,
perpendicular to the axis, so it will
yeah,
deflect in a curvy shape. But in the case of
yeah,
this cylindrical, so
yeah.
all are perpendicular to this.
Okay, so what do we call this phenomena? Like when plane sections do not remain plane in torsion, what do we call this?
Forgot
You
saying.
said it correctly. What is that? There is one word for that.
Yes.
So if I twist, so in this,
Warping.
yeah, warping happens.
Marking, yeah.
So my section will get deformed like this. So plane section is not remaining plane. So so things like this you can learn in this. advanced solid mechanics or the other advanced courses. So, but here we have only learnt about the uh, cylindrical shafts. So, in cylindrical shafts, when I apply twisting moment, I'll get only this. Uh, firstly, I'll take only. Firstly, I'll we are taking here the polar coordinate system, which is r, theta, and z. So z is in this direction. So r is here from center to this. The theta is obviously tangential direction. So here we are only getting uh, these stresses. What do you call them? Theta
What, sir?
shear stresses only we are getting. Or we are not getting any normal stresses. If we apply only torsion, we are getting the shear stresses. Like if I take an element here, theta z, and z theta. Obviously, right? Yeah, r theta or z theta. Yeah, z theta and theta z. If I take an element like this shear stress only which I will get uh, r theta z. Sorry, r theta and z here. My stress tensor will look like this: 0, sigma r, sigma r theta, sigma r z. Okay, so sigma theta z and sigma z theta. This is how my stress tensor will look like. And how will be the linear variation of shear stress due to torsion? It will be linear variation. So at the center it is 0, and at the farthest point from the center, the shear stress is maximum. And we have also seen the torsion formula, which is sorry, tau by r. We have developed this formula, torsion formula, which is tau by r equals to mt by ip, and we have got this g theta by l. Yeah, right. This is my torsion formula. Thing which we have to remember for competitive exams. Torsion formula. This is the angle of twist. This is the twisting moment, and this is the polar moment of inertia of the section, and this is the length of the shaft. Okay, this is the shear modulus.
Sir?
Yeah,
Sir, I have one question regarding the shaft and hole, sir.
shaft. Ah, yeah.
Sir, is there we call that is any projection we called as a shaft or any pocket shape if we called as a hole? It is not meaning that means the shaft should be always circular. It may be rectangular or it may be. What is the exact definition of the shaft and the hole, sir?
No, no, I didn't understand. What is the difference between shaft and hole?
No, sir. So if anyone
Shaft as
talk
a
about
whole. Okay, okay, okay. No, no.
if
Shaft is
anyone
something like shaft can be any shaft can be any cross section. It can be circular. It can be rectangular. Also, it can be any shape. Any cross section. Cross section might have any shape, and it also can be hollow. Uh, but when we say short, it means like it is experiencing torsion, some kind of torsion. Shaft is a member which is experiencing some kind of torsional movement.
okay, sir, and the hole also any shape.
Yeah, yeah, it can be any shape. It doesn't
Okay,
need to be. Yeah. Okay, so then we have gone towards torsion. We have learned how torsion will induce stresses. We developed this formulation, torsional formula. We developed, and then we have gone towards bending. And in bending, we have only uh, so when we have only seen the Euler-Bernoulli beam theory. So Euler-Bernoulli beam theory, as I said, it neglects the shear deformations. So in Euler-Bernoulli beam theory, plane section remains plane, and plane section uh, is also always perpendicular to the neutral axis. So that we have to remember that this is always perpendicular to the neutral axis. So we have got that bending formula, which is m by I is equals to sigma y by y, and this is the thing. And also you can say this is this thing also we have moment curvature relation also comes when we go for deflections. So r is nothing but uh, you can say uh, 1 by r is d square y by d. 1 by r is generally known as curvature. Rho is known as curvature. Here also in this course we have taken radius r also as rho, but in general it is 1 by r is known as curvature, and curvature is nothing but a second gradient of the slope. So we have developed this formula and we have seen that this is applicable for pure bending case. So only when bending moment is there. So when bending moment is constant, this formula was derived for that case. But we happen to use this for any case where bending moment is linearly varying or something. Like if I have a cantilever beam with applied load like this, my bending moment diagram will look like this. So, but if I take some at some point, like if I go to some point, I can use this formula to get the bending stress. I can again go to other point, I can use this formula to get the bending stress. Obviously, there will be shear which will be giving my stresses that I can use that I have to go again using the shear formulations whatever we have learned for shear. Uh, we have to get the shear stresses and we can sum it up like we can get them. So the main thing which also we should remember that whatever we have learnt in strength of materials is linear analysis. And when I say linear, it means elastic. And that means that when like let's say if I have done the tensile tension test, my stress strain curve will look like this. So in strength of materials we are only dealing in this zone, so we are not going towards this zone. So we are not learning what happens when we go in this zone. So we assume that whatever the load we apply, the stress is within the yield stress of the material. So that's why whenever something which is if I have something is linear, that means that I can use the principle of superposition. Okay, so like principle of superposition means like let's say if I have something like y is equals to ax, so x and y are linearly related. It's nothing but a straight line, right? Yeah. Something y is equals to ax. Let's say uh, if I take x is equals to 1, if I take x1 and x2, let's say if I take x2 is twice of x1. So let's say y2 is equals to a2 into x2, and y1 is equals to a1 into x1. So sorry, not a1. Yeah, y1 is equals to a into x1. So I am saying that x2 is twice of x1. So let's say if I substitute x2 is equals to 2 into x1. So I'll get 2 into ax1. Okay. So you can see that ax1 is equals to y1. That's why I can say y2 is equals to 2y1. So if I have x2 is equals to 2x1, x2 is nothing but you can say the input. If I giving the input as twice, I am also getting the output uh, as twice of the initial input. Okay, this happens only when have linear relation. Okay, let's say uh, let's say if I have let's say if I apply let's say if I have x1 and x2, uh, okay, like x1 or x2 and are some loads, and if I want to, if I'm applying them individually, and let's say now I'm applying uh, say let's say you can take another point with x3, and x3 is such that x1 plus x2. So y3 is equals to a into x3 because it is present on the line. It has to satisfy this equation. So let's say if I take x3 is equals to x1 plus x2, now I'll get y3 is equals to ax1 plus ax2. So ax1 is nothing but y1 and ax2 is nothing but y2, right? So my input is sum of two different inputs. Then my output is also sum of the outputs which this inputs individually give when they are applied individually. So this happens. This is called superposition, right? So I'm applying one load and I'm applying, if I have two different loads, like I'll assume I'm applying only bending and I'm applying only shear, and I'll sum it up. This is called, summing is called superposition. This thing I am able to do only because this relation is linear. So, linear, right? If I have, let's say, x square, so if I have y2 is equals to a into x square, obviously this is a quadratic relation, not really linear relation. So linear relation getting, so my graph will look like something like this, right? Y is equals to x square. So if I take x1 and if I take x2, so y1 is equals to a1 into x1 square, y2 is equals to a1 into a2 x square. Let's say if my uh, x2 is twice of ax1, twice of x1. If I substitute x2 in y2, so you can see that I'm getting 4a x1 square. So obviously you can say that it is 4 into y1 square. This is y1, right? So 4 into y1 square. So due to the non-linear relation, my output is not like input is twice of the initial input, but my output is 4 times of the sorry, this is y1. So, but my output is twice of the initial output. So, this is not a linear relation. So, when this goes like this, obviously, if I have two different inputs, let's say I have x1 and x2, it is equals to x3. If I substitute it, that also you won't get like I won't be able to solve it. So you won't get this will not be equal to y1 plus y2 because the relationship is non-linear. So superposition is not valid. So only in linear cases, that's why the graph is linear here. Only in linear cases we use a superposition. Okay, get this? You got this?
Yes, sir.
Yeah,
Sir.
yeah,
So generally, like in this course, we only took that linear part. That whatever that non-linear part is there in stress strain graph, do we use it like usually?
yeah. We do use it. There are advanced courses like they something like courses on nonlinear elasticity, plasticity. If you go to PhD or MS or MTech, you can take those courses and you can learn about them. So lot of courses are there like advanced things. So but in strength of materials, we only deal with these things. And also
So we
if you
can't
go take
ignore it.
no, we can't ignore it. Like obviously, if you if you take some structure and like you cannot if you take a aircraft, very high turbulence, everything it experiences. So structure might be having non-linear. It might be going to non-linear zones and all. Sometimes like you cannot restrict the load to only linear thing because see, if I want the structure to remain linear, like if I let's say if I have a small beam and I apply a load, let's say if it is if it is having plastic deformations, okay, let's but I want this one to but I want this one only to remain in if I want this beam to remain as an elastic beam, what I'll do is I'll increase the dimensions, I'll make the beam very big so that it is resisting more load. So if I apply the load which I was applying earlier, my beam will not bend like this, right? Like it is very huge. So you can say that due to the applied load, that beam is remaining in the linear region only. But the compromise which I have to do such so that this thing remains linear is I am using very high like a lot of material, so which increases the weight, which increases the cost of making the beam. Everything increases. So I cannot make that compromise every time. Like if I'm building if I'm building a aircraft, I want to reduce the weight as much as possible because if I reduce the weight, my fuel cost will be reduced drastically. So somewhere you have to make the trade-offs. So sometimes you want to go to that linear plastic zone also. Uh, Plastic zones like there are some like if you have rubber material like rubber, it is where like very it's not like and also there are viscoelastic materials. They don't have this uh, linear thing. Like if you extend a rubber, it is like some lot of deformation happens, like plastic deformation, something like that happens. So some materials do have that, like and also if we have these biomaterials like a skin, like skin, arteries, soft materials. Lot of soft materials are there. So there you will get this non-linear elasticity and different things. Sometimes you might have an elastic material, but this curve is not linear. Okay, then this is also non-linearity. So like even if you load it, it might come back to the original state, but it is not linear relation. Like I cannot give you one elastic constant. I cannot give you Young's modulus for this material. So elastic properties have to be elastic. Entire analysis, like you cannot use superposition. You have to do other things like very complex things, advanced process. So depending upon the material, depending upon the load condition, depending upon the structure, we have to do analysis. So like civil engineering, people want to stay in linear zones, but even though you want to stay in linear, like it is just an approximation. Sometimes you might want to go, like you want to save material and you want to go to that zone also, uh, because it is not called, like failure is not happening, right? Like material is very ductile, so it will go, it can go till I can use the property till this zone. So steel, if I have steel structures now, um, uh, steel structures, like you might have seen civil engineering constructions with steel. Sometimes people will go to till this point, like we take this bilinear elastic plastic curve. So we do that analysis. This is also linear, but yeah. So things will differ, what you want to construct, what you want to do. So obviously linearity is not, it is just that you are in this course, and basic uh, things will be learned first. That is the easiest thing which we can learn is linear uh, linear cases. So we are learning this as we go up, and like as we go to advanced courses, depending upon the thing, material or something, we have to again go to advanced courses and learn things. Lot of research is going on this in these things, like uh, non-linearity and all. Like not like it's not very uh, open field of research. Like you don't have perfect solutions, not even today also. Okay. No, and also we have seen, Devashish.
No, sir, clear, sir.
Yeah, okay. So then we have seen deflections also. So deflections are basically whatever we have seen, the deflections. They are also very small. So like not very high deflections, because we are, as I said, we want to stay in this course in the linear zones. So how, like we have seen different methods to get the deflections. Deflections is something which is known as like you want to know them because you want to know the serviceability. Serviceability is one aspect. Like if I have a bridge, I want to know the deflections at the in the bridge. Like I cannot make a bridge like which is bending too much. Like I don't want it to bend too much. So like it is not suitable. Like I cannot have a building in which the slab is bending too much. So I want to minimize the deflections also. So depending upon the structure. Okay. So we have learned about deflections, bending, and then we have gone to, we have also seen unsymmetric bending, like when we have bending occurring in two different directions, uh, unsymmetrical bending, and we have gone to, we have seen composite beams. We have then we have gone to theories of failure. Theories of failure are something, as I have seen, as we have seen yesterday, that theories of failure are useful when we are going to design any structure. Like depending upon the material, we can use this theories of failure. These are just theoretically theoretical predictions based on some property, like principal stresses or maximum shear stress or energy of the material. Uh, like I cannot. like if you have a material which is experiencing different loads, you can get the principal stresses, and using those principal stresses, and you use this theories of failure, which comes with some expressions, and using that we can get uh, we can see that if my um, stresses which are coming in the structure are within the permissible limits according to the theory, which may be maximum principal stress theory, or Tresca yield criteria, or maximum shear stress theory, or Moore Coulomb theory. So these are again we have seen that these are divided into uh, different theories depending upon the material, like and also depending upon the development at various stages. Like brittle materials, we use maximum principal stress theory, and again maximum principal stress theory is not suitable because brittle materials are very weak in tension, and but they are very strong in compression. So uh, an advancement to that is the Moore Coulomb theory. These two theories we are using for the brittle materials, and when we go for ductile materials like steel, something like that. So steel ductile materials have same properties mostly in tension and compression. So we have seen that ductile materials uh, don't fail by tension. Okay, so ductile materials mainly fail by shear. So that's why we go for maximum principal stress theory, maximum shear stress theory, and also um, distortion energy theory, which is called, which is also one mesh stress theory. So or octahedral stress theory. So it's like it is an advancement of the Tresca yield maximum principal stress, maximum shear stress theory. So ductile materials have different properties; they fail differently compared to the brittle materials. So that's why when we do tensile test for a steel rod, it doesn't fail like the crack is not perpendicular to the application of direction of load. So it fails like we have this cup and cone fracture, right? So that is basically it means that it is failing in shear. So ductile materials fail in shear. So remember that. So that's why we get the cup and cone failure. So theories of failure we have seen. So using this theories of failure, so we can design any structure so such that it doesn't fail, and it it remains well within the allowable stresses. So again, even if I take the stresses, permissible stresses according to the theories of failure, it might not be possible that I might get everything right when I build the structure, or when I fabricate the structure. There might be some internal defects, something which might happen. So that's why again we take the factor of safety, because when I put the structure into service, there might be some other loads which might occur, and effects I cannot predict. So again we take whatever the permissible stress we get from the uh, series of failure. Again we reduce it using the factor of safety, so that allowable stress is very much lesser than what is allowed according to the theory, so that my structure has that extra amount of safety which I can give due to the unpredictability of various things. Then we have gone to columns, stability of columns. We have seen how columns, long and slender columns, when applied with compressive loads, will buckle, and instability happens, or like they go into neutral equilibrium. So critical load, Euler buckling theory we have seen. So how is different end conditions we have seen, how they are going to give the uh, uh, effective length, different kinds of things, like how different end conditions will give change my load carrying capacity, different things we have learned. But it's like it's just an introduction to the columns theory. It is more like when we go to the advanced process, buckling is actually a non-linear phenomenon. So things, that's why we take deformed configuration while getting the buckling equation. So It's like we have just learned the stability of columns. When we go to the advanced courses, we learn different things uh, about buckling, stability, bistability, a lot of things are there. So that we will obviously, if you take any advanced courses, you can learn that. Okay, so like we have, I think, touched everything. I have tried to summarize everything. So we have learned whatever the things which we have learned. Uh, Individually, we have learned everything: torsion, bending, stress. But in an actual structure, everything can come in combined form. Like I can have axial, torsion, bending, everything I can have. Combined stresses might happen. There is also thermal expansion. Due to that, thermal stresses might have happened. Everything will come together, and because we are assuming that everything is linear, everything is in the linear zone, we can take the individual effects from each of the thing, and we can sum them up and get the resultant principal stresses due to the various things which we are getting. And if I get the principal stresses, I can say if the principal stresses is going towards the failure or the ultimate stress, and if it is going, if what to do, you take factor of safety to design the structure or not. So that can be done. So this is what strength of material, entire thing which we have covered in this course. Very, I think it was a very good course where you were seen, where you were given a lot of practical explanations with using the photoelasticity, and also various demonstrations given by professor in the class. So we have learnt a lot, including me. I have learnt a lot because I haven't seen this. Though I had the intuition, I thought that I had very good intuition about it. After attending the, after I have watched the lectures again in order to again teach in the, again clarify in the doubt session. So everything is explained very beautifully. And obviously, there are some things which are beyond the scope of the subject. Like you won't learn this in your college if you learn strength of materials. But it's like, uh, but it is always good. Like if you are in, let's say, if you are on the bottom, on the ground, and you are seeing something like a city. If you are seeing, if you are seeing a city from the road, and if you go to a tall structure and like a very high rise structure, and if you are seeing the city, you will get a good view of it. So I think this course does both of the things. Like you are seeing a very broad view from like a very high point, and you are getting to know different things. And that that thing, when you know that, when you see things from a very high perspective, it actually makes our understanding a little bit more easier, you can say, because you can connect different things, different dots you can connect. And if you connect like different concepts we are learning, so our understanding becomes more concrete, and we will be able to remember things for a longer time. So that thing is beautifully done, I guess. So I'll stop here. If you want to ask anything, you can ask. Okay.
Sir, I have
Yeah.
the uh, sir in the when we finding the stress tensor, so
Hmm.
we take one tetrahedron plane.
Tetrahedral. Yeah, yeah, yeah. Stress. Tetrahedral plane. Yeah, yeah. Okay, okay, okay. Yeah, yeah. Octahedral stresses.
Yes,
Hmm.
but we
Uh,
tetrahedron, no, sir. So we got a cube in with 45 degree. Then we got the plane with meet the three axes.
okay, okay. You are talking about this. Okay, okay. Oh, sorry. This you are saying?
Yes, sir. What is the geometrical name? Is it correct?
Yeah, yeah, yeah. Not,
Sir,
yeah,
what is
tetrahedron only. Not,
uh,
yeah, tetrahedron. Yeah. Hmm.
what is the purpose of taking this? Because we already know about the shear stress in the previous also.
No, it's like you are just taking some. Uh, I have a cube right here. I am just taking this like I am just taking it to represent a plane, some plane. Okay. So on this plane, you will have some normal stress and you will have some shear stress. Or let's say you will have some shear normal stress and shear stress you might have, right? Hello, Devashish, can you hear me?
Am I audible, sir?
Yeah, yeah,
Yes, sir.
yeah. See, initially we know only the stress tensor for this, right?
Yes, sir.
But this plane has some normal, and it is making some angles with this x, y, and z planes. Those are called direction cosines, right?
Yes, sir.
So, like you want to find out the stresses on this plane. If you want to find out the stresses on this plane, we
Yes.
take the stress transformation and we find out the different stresses which are present on this plane. Okay.
Understand, sir. And here also
Hmm.
Cauchy formula is useful for find out
Yeah,
the what is.
causes stresses. Yeah.
So that is for finding the shear stress only, sir.
Ah, no. Cauchy stress formula gives me the stress tensor, not stress vector. It gives sigma into n cap, sigma dot n cap.
Okay,
So
okay, understand, sir.
I have the stress tensor for this, and I know if I know the normal on this plane, if I do it, I'll get the stress vector like on this plane. Uh, what are the three different components of stress which are occurring? I can calculate.
Understand, sir. Understand.
Yeah,
Uh, clear, sir.
yeah.
Up to clear, sir.
Okay. Anything else?
No, sir. We cover all these things. From my side, it's clear. If Priyanka if asked something.
Okay.
Sir.
Yeah.
So regarding shear stress, sir, in Mohs circle,
Hmm.
while we are plotting along explain if it is along positive y-axis, then we take shear stress as positive.
Okay. Well, we have done this in the course. We have done like that. Uh,
So we are marking it in the bottom side, no, sir. Hello,
yeah,
sir.
yeah, yeah. Yeah. Tell me.
If
I'm
on
just.
positive unexplained, if it is positive shear, we're marking it on bottom side, and on y plane,
Hmm.
whatever shear we are getting, we are marking it on top side, above side.
Yeah, yeah.
So is it positive or negative, sir, shear that time?
Uh, just actually doesn't depend. Just check again.
Actually, in one of the assignment, there was question like this, sir.
Hmm. Yeah.
Like they have
I've
plotted.
seen. You had
Yes, sir.
asked this question in the forum, right? Something.
Yes, sir. I had asked in the forum.
Hmm.
So in the forum, they said that
Hmm.
about clockwise shear and counterclockwise shear.
Yeah, yeah, yeah. Yeah. So,
So my doubt was like we should take it as counterclockwise and clockwise shear while marking it, or we should take like whatever that professor said that at a point, if on X plane, if it is on Y axis, it is positive shear. If it is on Y plane and if it is along positive X axis, then it is positive shear, like that.
hmm. I think we have taken the sign conventions based on the this if the if on explain if it is in the positive y-axis, it is giving me anti-clockwise moment. So that's why here we are taking on x-plane we are taking this as negative, and on y-plane if you take, it is giving me clockwise shear, clockwise moment. That's why we are taking it as positive. This was the explanation given in the class, right?
In the class, like whatever in the video, I thought what, like when professor thought, I thought like
Hmm.
on x-axis, if it is like on x plane, if it is positive, then we should mark it on bottom side, and if it on y plane, if it is positive, we should mark it on top side. I thought it like that.
No, no. This is depending upon the moment which we are marking here. So this is giving me uh, anti-clockwise moment. That's why we have taken this as negative. Here on the y plane, this is giving me positive. Sorry, clockwise moment. That's why we are taking it as positive. The thing is, it doesn't matter. Like I can take this. In this course, we are following some convention, but it like you can take this as like this also. So this sign convention is not a thing. Like it doesn't matter a lot. So we don't need to worry about much. We don't need to worry about it much. Like as far as I know, I haven't like seen any trouble with taking positive negative. Convention is something like if you are doing a problem from top to bottom, you have to take the same signs. Okay. But here in this course, professor has given uh, this explanation only, that this is giving me anti-clockwise moment and this is giving me clockwise moment. That's why uh, things like they have taken negative and positive.
Okay, sir. Sorry, one more thing. I had asked it in the discussion forum also, sir. One regarding one question, sir. Assignment one question.
Regarding
Assignment one
assignment,
question, sir. Uh,
what was that question?
Udans, it was regarding the spacing in the coolant, sir. Circulating coolant in factory.
Assignment one. I'll just say.
Should I present my screen, sir?
No, no. I'll check.
Like I had posted like this, so like whatever I worked out, I had posted in the discussion forum. Uh,
Okay.
it was told about that about some radius I hadn't taken, but I thought I took it, but that's why I got confused.
Okay. Q&A. Week one, right?
Assignment one, question number 9, sir.
Okay. Okay. I'm just saying. Hmm. Uh, What was your assignment 1 and 2 types? Question number 9. Uh, So the question which you asked was in the question maximum pressure. This is the question, right?
Yes, sir.
Uh, what is the difference? What is the difference? That's the question, right?
What is the maximum pressure and maximum spacing
Okay, another question.
for circulating coolant in a factory? Engineer designed a pipe.
Yeah, you have asked. Okay, okay. I have solved question 9. With the attachment you have attached, right? Okay.
Yes, sir.
The displacement occurs rarely. Yeah, I'll do one thing. I have to solve this. I'll solve this and I'll post this in the forum only. Okay.
Yes, sir. Thank you, sir.
Anything else?
No, sir. Already completed sir course fully.
Okay, okay. Hello.
Thank you, sir.
Okay. Thanks for joining and making the sessions interactive. You hope we got to learn something from this course that we can utilize. Obviously, nothing goes wasted. Whatever you learned in life remains with us. So make sure that the only thing is that whenever we learn something, we have to revisit it at some point of time. Then only we remember things. So keep because you are having you are planning to do highest you are planning to do your higher studies or something else, maybe your job or something else. So something like repeated intervals, we have to keep revising things. So make sure you do that, and that will increase your retention. So neurological, it is a proven fact that when you do a particular thing and you stop it, like, and you come back after some time, um, and you do it again, practice something, so your neurons fire and make certain connections, so that they make the connection becomes even more stronger, and you remember those things, remember or understand things uh, differently, and more or more efficiently. And also things like whenever we learn something, like today we have learned something, uh, it's not like we have to, if we want to learn something, like we have to continuously keep doing it, um, like for certain days, and we'll get everything. So if we give some break and we'll do some other things and we come back to it, sometimes you get a totally different perspective and you get a new understanding. So spacing is also important, and also uh, revising things is also important. So make sure you do that, uh, and revise things, like whatever you have prepared, maybe let's seeing the lectures or revisiting your notes. You can do anything, and you uh, make your memory more strong and understanding more deeper. So I would suggest that you do this. Okay. Okay. Anything else? Can you hear me?
Nothing from my side, sir.
Okay. Okay. All the best for your interview. Do well. Uh, and like as I said, don't fumble. Like if you, even if you fumble and if you don't know, just say that you don't know. Don't bluff. And if you have learned something, tell them up to what you have read. And like obviously, don't panic in the interview. So sometimes what happens is that when they ask a question, and if you don't answer it at the start of the interview, like your whole confidence will go down, and you don't feel like remaining things also you um, like uh, like completely you can your interview can go haywire. So like don't worry, like if you get something, if you answer something bad at the start of the interview, see, like you can answer other things, remember that, and you can just like have that confidence, don't panic, and give the interview, and let's see what happens. Okay. Okay, chalo, we'll
Yes,
leave.
sir. Thank you, sir.
Okay, chalo,
So
bye,
best
all the
wishes to
best.
you too, sir.
Thank you, chalo.
And also
Devashish, all
good
the
luck.
best.
Good luck, Debashish.
Yeah,
Thank you.
yeah, Devashish, take care,
Okay, sir. When I
both
go
of
to
you take
IIT
care.
Madras, I meet with you, sir.
Okay, I look forward to meeting you. Okay,
Thank you, sir.
hopefully both of you get. Okay,
Yes,
chalo, bye.
Priyanka should also go now.
Yeah, okay, chalo, bye.
Bye, sir.
Take care, bye.